So for this next example, we've got an aluminum post that has a brass core in the middle. And it has an axial compressive load applied to it on a rigid cap at the top. And then we're trying to figure out what the average normal stress on the aluminum press is. Essentially what we're going to be saying here is that load is going to be kind of carried by the brass and by the aluminum. It's not necessarily going to be carried equally, however. So essentially, if we we'll draw a free body diagram of the cap itself. So essentially, we've got this 9 kip load at the top, and then we're going to have some sort of reaction from the brass. Let's call that By. And then we're going to have some sort of reaction from the aluminum. So, we'll just, it's equally distributed kind of around the ring. So I'm going to just kind of looking at it to represent it by AY over 2, AY over 2 on either side. But, overall, the net resultant of the reaction from the aluminum is also going to act through the same point. It's going to act through the centroid of its area, so it is going to be acting through the same axis as the 9 kip load and the BX. So again, if all we're left with this we don't have enough information to solve for what's going on here. We know that when we sum our forces in the y direction, that by, I wrote x there, didn't I? Let's by plus ay, that's going to be equal to 9 kips. So the total forces opposing that are going to be equal to 9 kips. But we don't know how those are distributed. We don't have enough information to figure that out at this point. Because essentially, if we took a moment to try to resolve that, because these both act through the same point, all you'd kind of be ended up with would be like AY over 2 is equal to AY over 2, which we already knew, or if we took a moment from here, it'd be like AY over 2 times the diameter plus BY times the radius minus 9 kips times the radius. So we'd only ever, we wouldn't be able to kind of differentiate that. We'd end up just with the same ratios as this. So that's all the information we're able to get just out of statics. But we do know that the 9 kip load is going to be shared amongst the two materials. But if we use the principle of superposition, so we can determine a compatibility condition that works. So again, if we're looking at this thing, when the cap gets pushed down, then the brass core and the aluminum core need to be compressed equally. So their strain or their displacement, their displacement needs to be the same. So displacement in the brass is equal to displacement in the aluminum. So that we can work with, right? So if we're working with that, then we can go ahead and say, so displacement of the brass, that's going to be equal to By times the length divided by the area of the brass times the Young's modulus of the brass. Whereas the displacement of the aluminum, that is going to be equal to the oh yeah, I guess I should specify since based upon the orientation of by and so on and so forth and ay on the containers, these are both negative, although to be frank, the negative sign does cancel out, but we should be consistent about making sure that our sign conventions are consistent. So anyways, ay is equal to negative, displacement A is equal to negative ay times the length divided by the area of the aluminum times the Young's modulus of the aluminum. So those two things, we've got by times L over AB times EB is equal to AY times L over A aluminum times E aluminum. So the L's cancel out because they're the same. So if we want to solve for one in terms of the other, let's solve for AY. So AY, that's just going to be equal to BY times A aluminum times E aluminum over A brass times E brass. So for the Young's, let's start with the Young's moduli here. I got the Young's modulus for the aluminum divided by the Young's modulus for the brass. So we just really need to know the ratio between the two. So that was given in the problem. The Young's modulus for the aluminum is 10 times 10 to the 3 ksi. The Young's modulus for the brass is 15 times 10 to the 3 ksi. So this ratio here, that's just 1 over 1.5. And then the area. So the radius for the brass core is 1 inch. The radius for the the radius for the aluminum outside sleeve is 2 inches. So the area, the cross-sectional area for the aluminum outside sleeve, that's going to be equal to pi times 2 inches squared minus 1 inch squared. So basically, taking the cross-sectional area of the entire thing minus the missing bit. Area for the brass, that's just pi over pi times 1 inch squared. So that's pi times 3 inches squared. This is pi times 1 inch squared. So that means that this ratio here ends up being 3. So we can solve for AY is equal to BY times 3 divided by 1.5. Which, I don't know why I'm bothering to bust out the calculator for that, but that's equal to 2. 2BY. So AY is equal to 2BY, and we still have our BY plus AY is equal to 9 kip. So 2BY plus BY is equal to 9 kip, which means that BY is going to be equal to 3 kip, and and the AY is equal to 6 kilo. So the sleeve in the middle is taking a bit more of the load than, the sleeve in the middle is maybe stiffer, but it's not taking as much of the load. And that's just because the outside sleeve is larger. It's got a larger cross-sectional area, so it's large enough to kind of overcompensate for that. So if we want to find out what we're asked for, we asked for the stress state, the average normal stress in the aluminum and the brass. So that we just solved for by using our P over A formula is equal to stress. So let's do the brass first. So that's going to be 3,000 pounds divided by pi times 1 inch squared. So 3,000 divided by 3.1415. That gives us 955 psi, pounds per square inch. And then the aluminum, so that's going to be 6,000 pounds. And that is divided by pi times 4, pi times radius of the outside squared minus the radius of the inside squared. That ends up being 4 inches squared minus 1 inch squared, so 3 inches squared. So 6,000 divided by 3.1415 times 3. That gives us 636.6 psi. So again, the aluminum was carrying a larger load, but it has a lower average stress level, which should not be surprising. They've got the same strain, so the magnet, given that they have the same strain and the Young's modulus in the brass is higher, we expect that the stress level in the brass for the same strain is going to be higher as well. Should be times 1.5. Yeah, it's 1.5 times as much because its Young's modulus is 1.5 times the Young's modulus for the aluminum. So again, the aluminum is carrying a larger load. That's due to its larger cross-sectional area. If they had equal cross-sectional areas, then the aluminum would be taking less of a load, but it would still have regardless of the ratios of the loads that are, regardless of what ratio of cross-sectional area you have, you're always going to get, in a loading situation like this, you're always going to get the brass to have a higher stress level because the stress is directly proportional to the strain, and in this case the strain is the same. So the strain's the same. Multiply that by the Young's modulus. The one with the Young's modulus, with the larger Young's modulus, is going to have the larger stress.